I forgot where I was. I'm Nick Kennedy, WA5BDU, licensed since 1962, so that puts me something over 60 years. Worked in the nuclear power business for 40 years, 40-something years, and then retired. And now here I am. It's quite an honor to be able to address a group like this, which has so many knowledgeable people, so I hope I'm up to it. I always like to start, if I get the opportunity to give a talk like this, by saying this is the golden age of homebrewing, and it really is. For one thing, we have so many excellent tools, free, like antenna analysis, circuit board layout design, filter design, and on, and LTspice is certainly among those. It only takes some investment in learning how to use them, which isn't always easy. But so I'm talking about LTspice. David asked me how much time I needed. I said 2 semesters, and I couldn't get that. So you're going to have to bear with me a little bit. I got to roller skate through this thing, which I tend to do anyway. I just don't want you to be dismayed if you're thinking, I'm not learning LTspice. I can't internalize all this. I'm really taking a test drive, and what I'd like you to see on the stuff about basically how to operate the program is that you can think, that doesn't look too hard, I can do that. And then if I get into some features you're not familiar with, maybe you'll think that looks interesting, maybe I'll give that a try. So here we go. That was my introductory. Oops. Oh, okay, we're there. Okay, this is my last slide where I let PowerPoint build it because I'm not graphically oriented, but how to get it. Essentially, you can go to analog.com/LTspice, and then it'll ask you to fill in some information, get a log on, and so forth, and then you can download it. The reason it's analog.com is, I think, or analog devices, but I think they bought LTspice, and that's why it's called LTspice and not ADspice. But thank goodness they kept it going for us hobbyists. Which way do I aim this? Okay. So I'm going to talk about the graphical interface, which is where you create your schematics, and you also put your spice commands on there. Talk a little bit about component models and libraries and third-party models. That could be a whole day itself, so I'm going to touch on it. But it is important. Talk about the major modes of operation of LTspice. It has 5 or 6. I mainly want to talk about DC analysis, transient analysis, and AC analysis. Transient analysis being time domain, AC analysis being frequency domain. And talk about choosing and entering the simulation parameters, features of the display plots, which is really where your output is when you run your simulation, and then maybe some unusual analysis types and some tips and tricks. Okay, if you're like me and you're starting a new program, you got a low threshold of frustration, the thing comes up and you go, I can't even do anything. Well, you need a piece of paper. So there's a toolbar across the top, and that plus thing is the new schematic button. You got to press that button. So that's all important to getting started. Once you do that, the rest of the toolbar lights up. And also, if you've already got a program or you're trying one of the built-in demos or samples, you can use that one to open it. Then continuing across the toolbar and placing components on the schematic. The basic stuff, resistor, capacitor, inductor, diode is in there for some reason, ground, voltage source is on the toolbar, and there's also hotkeys for each one. If you work with LTspice a bit, you're going to find those hotkeys are very useful. And a nice thing they did the last time they did a major update to the program, they did away with the old F keys for these operations and put in mnemonically related hotkeys like V for voltage, R for resistance, C for capacitance, and so on. And they're all pretty intuitive, except P for the component library. I guess I think of that as parts. That's the parts bin. And there's also an N to give a name to a net, which I guess is the right term. I think of it as a node, but I guess they're the same thing. And then when you click on one of these or you hit the hotkey, that component appears attached to your cursor. And that causes another anxiety attack. It's like stepping on bubble gum on a hot day. You can't figure out how to get rid of it. And you click on the page to put it there, but that didn't save you because it's a persistent thing. And there's another one attached. So you either right click on your mouse or you hit escape or you hit the next hotkey to go to your next operation to terminate that one. All right. And now, adding components and giving values. We're just doing something very simple here. I hit V or click the voltage thing. I hit R, and if I hit Control R while I've got a hold of it, it'll rotate 90 degrees each time. So I rotated that resistor. And I hit C for capacitor. Now my cursor is wildly looking around trying to find the ground symbol, and there it is. So I put a couple of grounds in there. Now I need the wire symbol, or press W. I click on the first terminal, I go to the next one and click again. If I got to make a 90-degree turn, I click at the intermediate point, and that works very well and very easy. Now to give values, I right-click on the body of the component. I put 10 volts in there. I'm really getting by. A 10K for the resistor, and then 10U, and LTspice understands that means micro, and so it puts the right symbol in there. This was just to demonstrate placing components. We're not going to do an analysis on this particular simple circuit, but there we go. All right, the various simulation types. You hit A for analysis, or you click the .AC button. It opens this panel, which has, I don't know, 5 or 6 tabs. I can't see that well. Transient AC analysis, DC sweep, noise, DC transfer, DC out point, transient frequency response. I've only used a few of them, and the transient and AC analysis are the main ones. We're mainly going to focus on transient and AC analysis today. Transient analysis is your primary tool for time domain analysis of electronic circuits. You know, if you took EE in school or somewhere else, and transient analysis may have meant charging a capacitor or discharging a capacitor along an exponential curve. Well, this is more than that. All your sinusoids, everything that's in the time domain is in transient analysis. And you can view the waveforms. Continuing on with simulation types, transient analysis is really like being on your workbench and looking with your oscilloscope at what's going on in your circuit. In AC analysis, you're going to view your circuit response in the frequency domain. This is especially useful with filters, matching networks, and passive circuits like that. But it's also very useful with especially small signal amplifiers. You're concerned with bandwidth and so forth, and it works well there as well, circuits with active components. In AC analysis, you're normally viewing, in other words, it's plotting voltage decibels relative to 1 volt versus frequency, okay? So like a plot for a filter response. You might be seeing gain in positive dB or attenuation in negative dB, or both, really, if you're plotting the frequency response. So I'm going to back up to defining a circuit or graphically creating a circuit. This time include a library component, which is a transistor, so I'll have to go to that parts bin thing, component database, and find it. I have a partially drawn transistor amplifier schematic, but I left out the transistor because that's the one kind of part I haven't accessed yet, and it's a huge database of parts. Even capacitors, inductors, you know, you can put the ideal one in, which I usually do, but you could choose a Panasonic aluminum electrolytic, and it'll give you the model for that. So if you're trying to get as real as possible, you know, there's cases where you want to do that. I'm also going to set up a voltage source for, it comes up just asking for DC volts, but you click advanced and you can create lots of waveforms. I'm going to create a sine wave to drive this amplifier. and I'm going to give a net name to a node that I want to be the output. One advantage of the net name is if you get a lot of waveforms on your plot, you don't know which is which. Well, you got a familiar net name here, V output, and you can find it. There's other advantages as well. I was going to show you how to fix the schematic that you got all screwed up, but I forgot to demonstrate doing that. But it's very easy to get your schematic completely off screen or too big or too small. You just hit the space bar. So that's super handy when you're working with the graphical interface. So here we go. This is supposed to be running on automatic. See if it's doing it. Yeah, there we go. I hit A or P for the parts bin. I selected NPN. I got a transistor. I drop it. This will run, but that's a generic transistor. So now I right-click that thing, and I say pick new transistor, and it's got a big list of them. We've got two old friends at the top, 2N2222 and 3904, and I took the 3904. Okay, now I think, yeah, this is where I'm going to create the voltage source for drive. I'm going to hit Advance, choose Sine Wave, put 10M. That's 10 millivolts. That's peak, not peak to peak, not RMS, for that sine wave. Frequency, I can't read it. I think it says 5E6, 5 megahertz. But anyway, now I click on N or hit N for the hotkey for the node to give a node name, and I type in V underscore out. It doesn't like spaces, so the underscore. OK, and I've got that thing stuck to my cursor. I'm going to put it over there on my output node of my amplifier. OK. Now we're going to continue on and do we're going to do a transient analysis on this thing by choosing the analysis panel or opening the analysis panel with the A and choose transient analysis, run the simulation. Before we look at the waveform plots, I want to show a nice feature where you can get the DC quiescent points, whatever you want to call them, bias points of the circuit. You put your cursor over a component, it turns into a current probe. And at the info line at the bottom, it shows the current through that component. And you put your cursor on a node, your cursor turns into a little voltmeter probe. At the bottom, it shows the voltage of that at that node. So you really don't have to run a separate DC analysis to see if you got your bias right. You can do this right from the transient analysis. When we do the analysis, I'll show the voltage, and then I'll want to show that you can also plot currents. So I'll move back to the schematic and put the cursor over the load resistor. It'll plot the current. Then at that point, I want to show you how you can add a separate plot plane. These plots are going to end up on top of each other. So right-click, choose New Plot Plane. It's going to give a split screen. And then I go, well, I better wait till I get there. I don't want to be talking. Okay, setting up the analysis. I only have to enter one thing, stop time, but I've actually entered two, I think 200 microseconds and 50 microseconds start and stop times. It creates a SPICE directive, and I have to click, put it on the page. All right, now I've run it. I got a split screen, so going back to full. And I'm really jumping around here, sorry, but maybe you can see the probe move, and you can see, once I get started, the current values appearing on the info line. There's R1, R2, R3, R4. And now I want to show the collector voltage and the emitter voltage. It's very fast, I know, but hopefully you get the idea. Now I'm going to plot V out by clicking on that node. There's my voltmeter probe. Oop, where'd it go? There it is. Okay, first thing I show is this is too dense. You can't see your waveform here. All right, so you can drag a rectangle across that waveform, upper left to lower right, and zoom in. I zoomed in. I zoom in one more time. Yeah, it tells me this thing is operating in a pretty linear range. It looked like a real sine wave at the output. Now I've come back and clicked on R5, and as I said, I got a current plot. There's a current scale over there on the right side, and the voltage scale is still on the left. But I can right-click in that plot pane, as they call it. It's hard to say. It creates a separate one. Then I grab that name or expression for the current, drag it down. Now we see them. It's easier to see that way, or can be. And we've got a current scale on the left of the lower one and a voltage scale on the upper one. Finished? Okay, some more things you can do. You can display voltage from point to point rather than the ground. If you just click a node, you'll get voltage to ground plotted. But you can click on a node, hold down your mouse button, your left button, and drag to another node, and your probe turns black, release it, and then it will plot voltage from one point to another. I want to show some stuff about cursor usage because they're super useful and you use them all the time in frequency and time domain. So I'll be using those a lot. I want to show how you can do an FFT of the waveform. Then you can see your harmonics. You know, we look at sine wave and say, yeah, it looks like a good sine wave. But if we do the FFT, we can really learn something about it. Then we'll do an AC analysis of this amplifier. So in this case, I think first thing I did was forgot I needed to run the analysis again. So I did. All right, I'm going to drag from the collector to the emitter. And then I'm going to look at the resulting tab for the plot. And basically, look at that expression at the top. If you can see it, it says voltage from node something to node something else. That's telling me that that's how it plotted it. Now I've gone back to plotting the output voltage. I click on the expression at the top. I get one cursor. I click on it again. I get the second cursor. That's all you get, but two is plenty. I want peak-to-peak voltage. So in the lower right corner of this information thing that pops up, I can see I've got 87 millivolts output, so I can figure the gain of this thing. Now I'm going between two crests. And again, at the bottom is the difference between the cursors. It's given me in time the period, and in frequency, it says 996 kilohertz. That's pretty close because I started with a megahertz. I already knew it, but if this were an oscillator or a mixer or something, you know, I might not know it. Now the FFT, that's on the view menu. It says FFT. Then it asks me which parameter you want to plot, but it highlights the one I'm currently looking at. So I say, do that one. It creates a separate plot pane, and it's really huge. So I zoom in. I see my fundamental, my third harmonic, and my fifth harmonic. I believe this is. I think the second doesn't amount to anything, so you don't really see it. I'm going to use the cursor to see how many dB down from the fundamental that third harmonic is. It's a little tricky to hit that small spike. You can use the left and right arrow keys. All right, got it there. And now again, we look at the difference between cursors, and it's something like 29.4 dB. So my third harmonic is 29.4. So this is a good fundamental use of LTspice to analyze this amplifier. You know, with this amount of drive, that's where we are as far as harmonics. Now we're going to do an AC analysis of the same amplifier. So I pull up the analysis panel. This time I click AC analysis. It wants to know, do I want, what kind do I want as far as scale? I want decade. I want, I think, 100 points per decade. I start at 1,000 hertz, and I'm going to 100 megahertz, I think. Click on Run. Click on the output node, and this curve is the frequency response of that little amplifier. Again, I'm using the cursors. I got number one. I'm looking for the -3D point, and now I remembered I need to park one in the middle first, so I'll have the mid-band gain. Now I move over and I say, move it until it says it's 3 dB off of that other cursor, and that shows me I'm 3 dB down from mid-band. Once I get there, I take the other cursor and match it on the high side And again, I go down and read that difference, and I see what frequency it is. I think it's 17 point something megahertz. No, it's really just a little audio amplifier, basically. I also wrote down the midpoint gain was 12 point something dB. Okay. Now, another AC analysis, this one I said this thing is so useful for, and it really is, and very accurate too. Now look at a crystal filter. I have a 5-pole crystal filter at 9 megahertz. I want to talk about the crystal component. It gives you a crystal component, at least it gives you a graphic symbol for it. But as far as LTspice is concerned, it's just another capacitor. In fact, it numbers them that way. That's because internally, a capacitor has series capacitance, series inductance, series loss resistance, and parallel capacitance, same as a crystal. So they didn't need a different model for that. It's just the numbers you put in there determine how it behaves. So I'm going to set up the AC analysis with start and end frequencies. This one's going to be more focused because this is the sideband width filter. I'm going to put a 1 in the AC sources analysis amplitude box. I right-click on that AC source, and over there it says AC analysis. If you've used Spice for a while and you're familiar with earlier versions, and I didn't realize the new version until I started preparing this, you used to put AC space 1, and now when you run those old files, you get an error. You don't want that AC anymore, so just take the AC out and put 1 in that amplitude box. Then we're going to run the analysis, view the plot, and once again use the cursors to show the bandwidth. And another really neat feature I think of this is that it will show the group delay of the filter. And if you've messed with filters, even I'm not an expert, but, I can read an article if it says you need low group delay to limit ringing. Okay, I want to do that. So to be able to plot that on here is very useful. All right, here we are with the crystal filter. First thing I do is right-click on that C1 because I'm pretending I can't stand calling crystals C, so I changed it to X1. I didn't do all the other ones, but I probably would have eventually. Now I'm putting in, I'm putting in a comment because if I come back to this thing 6 months from now, I won't even remember what frequency this thing was on because the frequency doesn't appear anywhere. So I put in a comment, this is 9 megahertz. Now I actually right-click on one of the crystals, and this is the list of parameters that I just listed a moment ago. One thing nice about LTspice, if you've measured a bunch of crystals, you can put in the individual values for each one. Oh, I'm getting away from myself. The voltage source, I'm going over to the right where it says AC amplitude, I'm putting that 1 in there. Got to be something in there because that's when it calculates dB, it's relative to that value. Now to the analysis panel again. This time I want a linear plot, total of 500 points. Start frequency, I think 8995 kilohertz, and stop frequency 9004 kilohertz. This is a 9 megahertz filter. Put that somewhere on the schematic. Then run it. Click the output node. Very nice looking plot of that crystal filter. By the way, that midband loss of 7 dB, 6 of that is due to internal generator resistance. So it's really 1 dB insertion loss. Okay, here we go again. I'm going 3 dB down on the low side from the midpoint. Again, it takes a little tweaking there. Gives me a chance to catch my breath using the left and right arrow keys again. Okay, now I see my bandwidth is 2.39 kilohertz. This is sideband width filter. And now I'm going to click in that right axis, which is the phase shift. When I do, this box pops up, and there's something you can check there. It says whatever I just said. I can't read it. It's group delay. And now that changed to milliseconds, and there's a plot of group delay. So very nice feature, I think, in LTspice to be able to see the group delay of your filter. Right. Now, creating transformers, there's not a transformer component, but it's super easy. You just put 2 or more inductors, and then you give a SPICE statement that tells how they're linked as far as mutual inductance. You assign inductance values according to what you already know about how transformers work. This is going to be a 2-to-1 winding ratio and voltage ratio and 4-to-1 impedance ratio. So I make the inductance of one 4 times the inductance of the other to achieve that. Use the .t button or just press the period to create a SPICE directive. K, in this case, it's going to be K1. L1, L2 is the 2 inductors that are linked. And then that lowercase k is your coupling coefficient. Typically, it has to be between 0 and 1. And for toroids, tightly coupled, usually use 0.99 or 1.0. There are polarity marks on those windings. The old SPICE didn't show them until you created that K statement, but now they're always there. So according to your design, if polarity is not important, don't worry about it. If it is and it's wrong, use the move command, grab one of those inductors, use the Control R command to rotate it, and then put it back in with the polarity dot going the right way. At the bottom here, I say a 3-winding transformer might be K1, L1, L2, L3, 0.99. For instance, you have a center tap on one side. That's going to, you create that with a 3-winding transformer. So here's a transformer. I've got 7 megahertz, 1 volt peak on the primary. And I'm creating this, the link statement, K1, L1, L2, 0.99. I say OK. It's attached to my cursor. Put it right up there between those 2 windings. Is a good place for it. Now I run it, and I look at the output. I can just move my cursor up there, and it'll show me at the bottom the peak voltage is about 0.485. I said this was a 2-to-1, and it's 1 volt on the primary, so I shrug and say, well, that's close enough, but later I'm going to ask why I didn't get 0.5 volts and see if we can do anything with that. Oh, wait a minute. That's something I didn't illustrate, so I was just going to tell you that. I tried a couple of things. You give those windings a resistance, or you can. In some cases, you have to if you just have a voltage source and an inductor. So I gave it 1/10 of an ohm. So I went back and I said, let's make it 1 milliohm. That didn't change anything. I'm going to show later how you can make the time increment smaller. I did that. That didn't change it. So I thought, what about the 0.99? I changed the 0.99 coupling to 1.0 and ran it. Now I got 0.5 volts out as expected. So the lesson to me was there's a difference between 0.99 and 1.0. So that's something you kind of might want to keep in mind. Maybe you know how tightly coupled your windings are. You know, it doesn't have to be one or the other. Maybe it's 0.995. So that's something you can fine tune. Okay, now I'm ready to move on from that one. I've got a few odds and ends to talk about. One is waveform math. We've been plotting things, and there's a node or something at the top. But waveform math is a powerful tool. You right-click on that expression at the top of the plot, and you can multiply one waveform times another. You could square a waveform. You can multiply it by a scalar. Maybe you've got one that's big and one that's little. You multiply that little one. Of course, you change the amplitude, but now you can compare them a little easier. So you could divide a voltage by a current, which we're going to show you, and we expect ohms out. Then there's a power measurement tool in the transient analysis. You'll put your cursor over an element, either a voltage or a source or a resistor or something that has resistance. You'll hold down the Alt key and click. So when you do that, instead of plotting current, it will plot instantaneous power. And then there's a way to read average power from that. Also going to talk about specifying the maximum time step, which is an option statement you put into LTspice. There's two types of text on the schematic. You probably already noticed. The black is actual SPICE directives or commands or whatever you call them, statements that affect the analysis. And then in blue are your comments. So you're free to be liberal with those comments because you're going to come back later and ask what the heck this is. Now here's a simple circuit. I've got a sine wave set up with the equivalent of 10 volts RMS, and it's going to a 100 ohm resistor. So I expect 1 watt, 10 squared over 100. All right. See the cursor turned into a thermometer. I hope you could see that. I don't know if you could or not. That's telling me we're measuring power because I'm holding down Alt. Now, I looked at this plot. Okay, I can't get a whole lot out of that. That's instantaneous power. But if I right-click on it, it'll give me a little information box. And one of them is the average. That's the same thing as RMS. So I think I'm seeing 964 milliwatts. I expected 1 watt. Okay, so I want to hold that thought. I got some more waveform math, but we're going to come back to that, why I didn't get a little closer to 1 watt. Now I've plotted the source voltage again, the sine, and I right-click on it, and I've got a expression editor. So I'm going to say that waveform times itself to square it. Because I think most people are going to know that when you multiply a signal by itself, you double its frequency. And that did happen. Just to illustrate, I went back and plotted the input or the source frequency again. Now I zoom in. If you can see the red, yeah, I guess you probably can. You can see that it's half the frequency of the other one. So I was just demonstrating squaring that waveform. But something a little more complex maybe will be to take that waveform from, it's basically just the source voltage, and divide it by the current coming out of it. That's the current to that resistor that it's connected to. And I'm thinking, well, it's going to give me something like ohms. Well, it's a pretty ugly plot. If we zoom out a little bit, okay, there it is. It's real spiky. It seems to be centered somewhere around 105 ohms. I expected 100 ohms. So now we're going to move into the thing where you can tell SPICE what the maximum time step. It guesses and it does a good job. But sometimes you see some results that aren't quite right, and you might want to tell it, so I'm going dot options, max time step, I believe, equals 1e minus 5. That's going to give me 100 samples or calculations per waveform, which I hope is faster than what it had been doing. So I run the analysis again. I do the power thing. And now look, I've got a straight line, and it's lined right up with 100 ohms. So that really improved that a lot doing the maximum time step. And recall the power measurement before. We're going to do that one again, having run the analysis at that time step. And now, when I right-click on that instantaneous power waveform and read it's 996 something. So what I've calculated out, it's going to pop up there in red. You can see it. Well, I think it went from 6.4% error to 0.36% error. So that's just another tool to keep in your hip pocket. If things aren't looking right, you can consider changing the maximum time step. Okay, here's a good spot to put in something about importing third-party models. There's a huge database, but they're mostly LT type devices and AD devices. There's some Maxim devices. A lot of cases, in my case at least, I'm doing like a proof of concept or something. So I might say this LT1015 op amp is just as good for my purpose as the TI op amp I'm really using. But sometimes you want the real thing. So you need to import a model from the third party. The intrinsic devices are are the easy ones, like NPN, PNP, JFET, positive and negative, NMOS, PMOS, and diode. For one thing, they all match the internal symbol. Now, more complex ICs use a sub-circuit definition, and one thing that makes it more complex is their packet. You got to have a symbol, and its pin numbers have got to match up right. But we're just going to talk about a common op amp. Well, the first thing we're going to talk about is a transistor. That's easier. Find a model. You can do a web search, like on the SPICE model. For parts that are in production, typically you could go to the vendor site, you could go to Mouser, you could go to DigiKey, and it might give you the SPICE model, the symbol. It might give you the footprint for KiCad and all that good stuff. But we use a lot of stuff that's 20 or 30 or 60 years out of date, you know, so, but all those stuff, that stuff's still out there. You're just not going to the vendor. You're going to other hams, you go into the LTspice users group, and there are huge databases out there. And when you find one, don't just take that one. Take the whole thing. You know, if somebody's got 500 old transistors, you know, take the whole database. Build up your own library. As far as how to use it with the transistor, I say 2N20 or 3053. The SPICE model just consists of plain text. So you can take that text and space it or paste it onto your schematic with that dot command. And then when you put a transistor symbol on, you have to right click it, and where the value field is, you would type in the name for the transistor. It's the name that appears in that text, which might vary a little bit from the common name, so you kind of got to look at that. The other thing is to save that text in a file and use a .include statement to tell it to look for that file. You programmers use the include statement for libraries and stuff. It works that way. And, you know, no sense in having a single file, so you create your own file. Well, we're going to talk about that. An old trick with LTspice was to take your transistors and stuff, and you have access to the databases, component databases that the system gave you, and so you just paste yours in there, and now it looks like it's part of the system. But they discourage that because LTspice updates pretty often, and when it updates, it overwrites that, and you come back 6 months later and you go, hey, it won't run. I can't find my transistor. Well, the latest version of LTspice, they've thought of users, and they created files called user. They have their file, I forget what the base name is, but it's .bjt, but you can create one your own called user bjt. It will look for that. It will treat the transistors that are in there the same as the transistors that were in that database. So when you click on transistor, and you'll find it in there. And it's not just transistors, all those fundamental intrinsic type ones, you can create databases for those. Now we're getting slightly more complicated with an op amp, because an op amp has a model statement. But the example of this 5533 or 5532 op amp, it's not too tricky, because you can go to the parts database, and you go to op amps, and there's a list of millions and millions of LT and AD. You go all the way to the end, and there's like some generic perfect op amps, and then there's a couple that are just for a symbol. In this case, I take op amp 2. There's one that doesn't have power pins. I can't use that one. It's got to have power pins. So I take op amp 2, paste that in, and then I type NE5532 into its value field. And you know, we could go a long time talking about importing models, and I wish I had time to do more. I also wish I knew more about it. But I want to move on. I talk about DC sweep analysis. I said I really only basically used the 2 analyses, but this one I picked it because, I guess because it's kind of fun to play with. You can sweep up to 3 DC sources. Here I got a simple transistor with a current driving the base and a voltage for the collector. I'm going to sweep the collector voltage from 0 to 15 volts with a 0.1 volt step, and sweep the base current from 0 to 100 microamps in 10 microamp steps. And when I choose that DC sweep, it gives me these little panels that says, which source do you want to sweep? I say V1, 15 volts, 0 volts to 15 volts, 0.1 volt step. And then I say I1, 0 amps to 100 microamps, 10 microamp step. Then I run it, and we get this familiar for most old timers who have looked at textbooks, and you've seen what they call characteristic curves for tubes and transistors. So along the bottom, I've got the collector voltage. Up the left axis, I've got the collector or emitter current. And then each one of these curves is for a different value of base current. If I hit Shift S, it gives me the list of them. I don't want to see them all. I can highlight one or more than one and say OK, and it will just show those. So that was fun to do. I'm not sure what. I haven't used it for a practical reason yet, but I thought I would demonstrate it. Another cool thing you can do in LTspice is specify initial conditions. You can specify the initial current in an inductor or the initial voltage on a capacitor. This can be in a circuit with other sources, or it can be in what they call a source-free circuit. So use the SPICE statement again, .IC for initial condition, and then in parentheses L1, I want this in this inductor equals 1, tells it 1 amp, or .IC V of C1, capacitor, I left out my equal sign, oops, equals 5 volts on that capacitor. I've heard some people say they've used this thing to coax a reluctant oscillator into starting, which is weird, but I think maybe I've done it myself. It's also useful to see if a circuit that's just is source-free will ring or will it just decay away. I talked about transient analysis earlier. This example rings with the decaying sine wave because that looks cooler. But with a smaller value of resistance, it'll just simply decay off with no ringing. And with a large resistor, it'll ring for a long time. Okay, I put my initial condition statement in there. I also have a transient of 38 milliseconds. Initial condition, L1 equals 1, so it's going to have 1 amp going through that inductor. And when I run it, I get this nice decaying sine wave. It's ringing like a bell. I don't show it here, but I use my cursors, and yep, between the crests, I see the frequency is what you calculate from that value of L and C. Okay, another technique to vary a value with step statement. What do I mean by value? Well, it can be most anything, the resistance, capacitance, inductance. It can also be voltage value. In this case, I'm going to go back to our friend, the one transistor amplifier, and verify the drive voltage. There's a couple of ways to do this step statement. One is with the list word in there, and you just list the values you want. The other is you give the initial and the final and the increment. These two I show here are equivalent. They go 500 at a time. But you know, if you wanted some that weren't equally spaced, you'd obviously use the list statement. If you want equally spaced, you'd probably leave that out and let it space them. This example, we're going to drive this amplifier from 0.1 volts max to 1.6 volt max in steps of 0.5 volt. And what I'm looking for here, and this is something I use SPICE for a lot, is when does waveform distortion start? If you're building an amplifier, you know, you want to know a lot of things about it, and one might be how much power can I get out of it before it starts to distort. So I've run the thing, and sorry. I have not run the thing, but there we go. And so it's showing them all on the same page. So obviously the one with 0.1 volts drive, 100 millivolts, is that one. There's the next one, the other red one. I don't know if it's called red or not. Looks like we're maintaining fidelity until we get to that last voltage, 1.6. We've got some clipping here, and we've got some waveform abnormality down there. So that's kind of telling us, you know, having seen that, if I wanted to, I could focus in closer, and, you know, I might have some criteria I'd set. I might say that waveform's okay, or maybe it's not. It depends on how I'm using this amplifier. But very useful step statement. Okay, another thing that's cool in LTspice is using a transmission line as a circuit element. There's two types. One is lossless, which I'm doing here, and one has loss. It's very easy to define at first. You give it a characteristic impedance, that's the easy part, and you give it a length, but the length is a little tricky. The length, instead of the actual physical length, you give the amount of the time in seconds it takes for a wave traveling at 300 million meters per second to traverse this thing. And so now you got to back up, scratch your head a little bit, and get out the calculator, which I did. And I figured out a quarter wave at 5 megahertz is 50 nanoseconds long. So I've put this in, and to demonstrate this, I want to use, we're mostly familiar with quarter wave matching sections, so I have a 100 ohm load. That's a mandatory resistor, by the way, so I stuck a 10 gig ohm. You got to have that past the ground. Then I have a source resistance of 50 ohms, and we expect that thing is going to match that 100 ohm to that 50 ohm. So we'll just have to look and see. And we're doing an AC analysis from 100 points from 1 megahertz to 10 megahertz. I forgot to say that, and it's important, on units, SPICE is case insensitive. So 10M lowercase is 10 milli, it could be volts in this case, or cycles, and 10 capital M is also 10 millivolts or whatever. So if you want mega, you need to type MEG or you type E6 or something like that to tell it you want mega, because you'll end up asking yourself, what the heck's wrong here? So, all right, we're going to run this thing. And so I see, I'm looking at the voltage on the load, and this is a AC analysis. I've moved my cursor over there towards the peak, and that little info box, wherever it is, it tells the frequency it's 5.00. So, I said I cut this thing for 5 megahertz, and that is, in fact, where I'm getting the peak power transfer. There are other interesting things you can play with here, just for fun or education. This is a sine wave, of course, because I'm doing AC analysis. You can go into transient analysis. You can launch little nanosecond wide pulses, and if you're not matched on the far end, you can see them coming back. Now, you can't probe inside that transmission line, but you can make one out of several transmission lines. You can look at those points, and it's fun to see that on the graph. It went this way, now it's come back this way. It's shorter. Very educational for you nerds. Okay, this may be my last amazing thing. You can output waveforms to a wave file, and I think most people know, especially if you've messed with audio or you played a CD, a wave file is an audio file, and you add a wave.wave directive to your schematic to create the wave file. The format is .wave, double quotes, file name .wav, number of bits of resolution, number of samples per second, and the name or names of the signals you want to be in this file. Now, an example, .wave, my file .wave. Now, 16 bits of resolution. That's a standard for audio, so that's a good thing to use. And 44,100 samples per second is also the sample for, or the standard for the audio on your CDs, for instance. Now I've listed here V-out. That would create me a mono file. I could list 2, and I'm going to in my example, and it would create a stereo file. I can also list lots more. And if you're in the data analysis, maybe you can figure that file out, but I don't think your music software is going to figure it out. And maybe it's quadraphonic, I don't know, whatever they called it. So here's an example. I thought I would take a square wave over here on the source. That's 600 hertz square wave, 1 volt peak to peak. By the way, this thing wants no greater than 1 volt, so watch that. I've gone archaic here. I've got RC filtering. Got 3 stages of RC filter to try to make that raspy sounding square wave down to something approaching a sine wave. And oh, by the way, it reduced the amplitude by 1/3. So a little bonus thing for you. This gizmo here is I forget what they call it, dependent voltage source or something like that. But basically, I told it to multiply this voltage by 3.33 because I wanted the amplitudes to be the same. I'm going to plot this square wave coming in and this sort of sine wave going out. I say plot. I'm going to output it to a wave file, and I want them to be the same size. So I run that, and how to show it to you, I'm not going to play it on the speaker, so I use some software. It's called Audacity. It's a shareware or whatever they call it version of Cool Edit, at least in my opinion. Very nice software. And the left channel there, you see the 600 hertz square wave, and then below that in the right channel, you see the almost sine wave. And so that's, that's how that worked. Oh yeah, another thing, I have not done it, but I understand you can use the waveform as an input to your circuit too. So it sounds like you can take a receiver or whatever, maybe set it pretty broad and you're listening to something pretty nasty and you make a recording of it, make that recording a wave file, and then put that wave file in your SPICE simulation, and you've designed some cool thing to filter that stuff out, and then you can look at how that came out. So that sounds really interesting and useful. Resources for learning. Boy, things have gotten so much better since the last time I talked about this, because like for Arduino or anything else, you just do a Google search and it's like, it's customized for you. So, but there's built-in help, there's examples. Analog.com has demo circuits and videos. There's a huge users group on Groups.io and some very knowledgeable people. Really smart. I'm intimidated by them. I'm real careful before I post anything. Read their posting how-tos and don't mess up, or they'll tell you how you're supposed to have done it. But they are very, very helpful. For some reason, I wanted to come back and summarize the shortcut keys because they're so useful, but I'm not going to try to go over them because I'm sure I've probably used up more time than I should have already. And so, wait a minute. Well, I can't get to the end. The end. Thanks for watching.
We have time for maybe one question.
An easy one.
Hey, do you know if there are any component libraries for common thermotrons?
Yes. I mean, I've seen people doing it in SPICE. I haven't done it myself, but I know people have developed some tube models and done it. So if you search around, you'll find them. How good they are, how accurate, I'm not 100% sure. That's true of, I'm going over here, but I tried to use a 1N4007 for a pin diode. It didn't work. Turns out they left out that parameter for carrier lifetime. Okay, the end. I'll go. Yep.
Thank you very much, Nick.